Welcome back to Coronavirus University. Thought I'd wrap up with something familiar, really back to the ABCs, or rather back to the AMTUVWs. Um, I've got here a familiar set of objects, namely the letters of the Roman alphabet, but I've written them in a way that sort of maximizes the symmetry of each one of the letters, and I've grouped them together into groups that have the same symmetry matrices. So I call these the symmetry matrix groups of familiar things, and the letters A, M, T, U, V, and W have the following thing in common. If I center them, the center of mass at the origin, 0, 0 in the plane, then the identity matrix and also this reflection matrix that sends E1 to minus E1 is a symmetry of each of those letters, at least if I've drawn them in the most symmetrical way, and I intend that. Similarly, the letters B, C, D, E, and K have, again, the identity, always the identity, but also this reflection that sends E2 to minus E2. And these are reflections. Reflections mean that they're equal to their inverses. In other words, their square is the identity. Well, that's not quite what a reflection is, but it's roughly that. The next collection of letters that we get to, this is sort of a shuffle. Everything is increasing in order in the usual order of the alphabet, but we've shuffled things. F, G, P, and R are the only letters which I think, regardless of how carefully you write them, they only have the trivial symmetry matrix, namely the identity matrix. And then a little exercise is find the symmetry matrices of the letters H and the letter I, which kind of look like each other a little bit. And it turns out that there are 4 of them, including the identity. So the identity is one of those, but you should find out what the other 3 are. And then that's supposed to be a letter J. I've written it, maybe you'd find that on an old-fashioned liquid crystal display or something. And a Q, written sort of maximally symmetric. Well, that has a mirror plane or mirror line this way, and I'll let you figure that out. There are 2 of them. One is the identity, and then you have to figure out that matrix there. And the other one that's very similar is the letter L, written in its maximally symmetric, recognizable way. Again, it's the identity in a reflection, except this is the reflection across the line where x1 equals x2, or E1 and E2 get switched. Okay, so same remarks as above there. Oh, and I guess one more, except this one's not quite the same. This one's kind of more interesting. So N, S, and Z, or Z as some people say it, those aren't symmetric with respect to reflections. They're reflection with respect to some people call inversion, or, well, there it is. It's the identity and minus the identity. So the difference between a reflection and inversion, this also has the property that its square is -1. It's rotation by a half turn, if you like. But the fixed set, in this case, is a horizontal line. In this case, it's a vertical line. And here, the fixed set is just what? It's just the origin itself. Okay. And then the only other one that I did was this one, because if you write the O as symmetrically as possible, it really is rotationally symmetric, but also it's symmetric with respect to reflection in any plane. One of them implies the other in some sense. And that's this complicated thing here in this kind of lavender color, where I've got all the rotation matrices where C is cosine and S is sine, so cosine squared plus sine squared is 1. But also, for the same cosine and sine, we have all the reflection matrices. So actually each one of these sets is, if you like, geometrically a circle. All the rotations correspond to a circle, and these other reflections correspond to a circle, if you like, the circle of where the mirror planes are. So the symmetries of the letter O, or the circle, is actually two copies of the circle geometrically. One the rotations and one all the reflections. That actually has a name. It's actually a group in the purely mathematical sense. This is known as the group. This group here is known as O2. Okay, so it's the orthogonal matrices in 2 dimensions, 2 by 2 orthogonal matrices, O2. So this actually has a name. This whole thing. And this part here, where the only have rotations, the rotation part, which includes the identity. The identity is where the angle is 0. It's called SO2. So this is the component that contains the identity. So the identity matrix 0, 1, 0, 0, 1 is in this component. Okay. Some people call it the identity component of the orthogonal 2 by 2 matrices. In fact, all the symmetries, all these symmetry groups, if you like, sit inside O2. And the only one that sits inside SO2 besides the trivial one, I believe, is this one, the symmetries of N, S, and Z. Okay. And then there are two more, actually fairly large symmetry groups there for the letters X and the letter Y. Okay. The Y, if you make it very symmetrical, it's more symmetrical than A or M. If you make it kind of not like this, but exactly equal angles, then there's an interesting threefold symmetry. So this has a threefold symmetry. So you're going to get quite a few elements there. You might think about how many. And X, similarly, if I make all these angles equal, then you have a big symmetry. I think this one has 8 elements and this has 6 elements, but you should check that. Okay, so that's it for the plane. Maybe you can think of some other objects in the plane that you'd like to explore. But I want to finish with some objects in 3 dimensions that you may be familiar with. So this is one that actually is related to a very potent greenhouse gas. Greenhouse gas, okay? You know what molecule has the symmetry of the regular tetrahedron? This is a tetrahedron, regular tetrahedron. Well, it's one of the more common molecules in the universe, actually. It's a methane, CH4. So not a carbohydrate, but rather a hydrocarbon. There's no oxygen in it. So methane has this symmetry. Because it has so much symmetry, it can basically reflect a lot of energy or trap a lot of energy. And it turns out it's in the infrared part of the spectrum. That's why it's a greenhouse gas. Well, this tetrahedron actually is a little bit hard to analyze. Clearly it has some threefold symmetries. There's the RBG symmetry, if you like. There's that threefold symmetry there. Okay. In fact, around each vertex it has threefold symmetry. And it also has some mirror symmetries, just like a triangle does. It's mirrors like that. Also has, I guess you can see the mirror like this also. There's a mirror like that. Okay. But if you want to write down the matrices for it, it's sort of convenient to put the tetrahedron inside a cube. And if you were to do it like I'm doing it, I don't think I can make the colors line up, but notice I've got an edge of the tetrahedron that goes from white to green or green to white. And then I've got another edge that goes from yellow to black up top here. And the yellow to black one. Okay, so that uses, I've got the colors on the vertices of this cube arranged so that exactly 4 distinct colors correspond to one way of fitting the tetrahedron inside the cube. And there's another way of fitting inside the cube, which is, I'm just going to switch it around. So there's another one like that. Okay, so now the white and the green are up on the top, and the black, and the orange are at the bottom, corresponding to the vertices of tetrahedron at the bottom. So there's actually a tetrahedron that sits inside here using half the vertices, these two here and these two here, and the edges of the tetrahedron then become face diagonals. And this cube, I want to make the center at the origin rather than the cube with one of the corners at the origin. So let me replace this cube in your minds with this cube that you've seen before, namely the cube that has one of these little white blobs at the origin, and then here's the green blob at E1, the red blob at E2, and the purple blob up at E3. I don't know if you can see that. Okay, so in this configuration of the cube, think of this as the cube again. This vertex here is at 1, 1, 1. Okay, 1, 1, 1. And I'm going to choose that vertex as one of the vertices of the tetrahedron. So I'll put the tetrahedron in there again to sort of give you some idea of the orientation, but it's a much bigger one. It's a tetrahedron that goes from here to here, and then at the bottom, I'm going to choose the opposite pair of vertices. So what are the vertices there? I'll just say it. I'll let you think about this in your mind. Okay. One of them is at 1, 1, 1, and the other ones actually have two minus signs. So the ones down here, right, the last coordinate is -1. So this one might be, guess if I'm doing it the way I have it, it's 1, -1, -1. That's this one. And this one would be -1, 1, -1. There's one more vertex up here. What's that one? Well, only one of the coordinates is positive. That's the third one. So it's -1, -1, 1. And so you can think of the tetrahedron as the vertices of the cube. There are 8 of them, but only 4 of them have an even number of minus signs. Okay, so this one has no minus signs. It's 1, 1, 1. The other 3 have 2 minus signs. And that's the only choices. So you might think about what matrix takes this vertex to this vertex, but fixes these other 2 vertices. Okay, how would you find that matrix? Well, you want to figure out what it's doing to E1, E2, and E3. And if you write this vertex as E1 plus E2 plus E3, and similarly with plus or minus signs for the other vertices, you can work out what if I interchange these 2, for example, and fix these 2, you can work out equations for where E1 goes, E2 goes, and E3 goes, and that'll give you the matrix for it. So the challenge is to find the matrix of symmetries for this guy, and I'm going to give you a hint. It's a pretty big set of symmetries. Depending on whether you allow reflections or rotations, it's either 24 or 12. If I allow reflections, it's that, or it's, if I don't allow reflections, then there's just 12 of them. And as I said, there's some of them which are a little more challenging to see. Like, so for example, if I'm going to, here's 1, 1, 1 again. I'm going to hold this towards you. That's one of the vertices. Here are 2 more. So there's a triangle here. This one. So my nose and my 2 fingers, my 2 hands are holding a triangle. And there's a threefold symmetry that takes, one to the other. Okay? I don't know if you can see that, but Okay, so there's a threefold. So that's another symmetry. That's a rotation. And so you might figure out why 12 is the number of symmetries for that. It's somehow related to the fact that there are 4 vertices and they can do a threefold rotation about them. But let's see if you can do that. It's a big set of symmetries. And now I could go bigger. I could just look at the cube itself. Okay? Okay, so the cube itself. And the cube itself has, I don't know how I've oriented it again. It's this original orientation. It has a lot of 4-fold symmetries, unlike the tetrahedron. Okay. Well, we did this before. But there are also 3-fold symmetries. And there are a lot of reflection symmetries. And those are easier. So you might start with a cube. And I'll just tell you a little bit more about the cube. The cube turns out to be, if I allow reflections, it has actually 48 different symmetry matrices. These are all 3x3 matrices. And if I only allow rotations, it's that. So, by the way, the 3x3 rotations also has a name that's sort of analogous to this. And so this is the part that's in. The second one is in what I call SO3. These are the rotations in 3 space, and that sits inside the rotations and reflections of 3 space, the so-called orthogonal group of 3 space, O3, in the same fashion. There are twice as many reflections as there are rotations, although both of them are infinite in number. Okay, but if you end up with something like the tetrahedron or the cube, there's the finite version of that. And those are some of the interesting ones. You might think about if there are other crystals that you like, but of course the master of them all, the most symmetric thing of all, is the celestial sphere here. Some stuff inside there, and that one actually has all the rotation and reflection symmetries of space. And so it's that one there. So that one you might try to write down something analogous, all the 3x3 matrices, in a similar way that we wrote down all the 2x2 rotations and reflections. Okay, so that's a little bit of what I might call this is really a challenge problem. So it might even be worthy of a milkshake if people do it. So it's challenge problems. Some are a little more challenging than others. Try to figure out these symmetries. I hope you have fun with that. Good luck on the exam.